So thanks for coming, everybody. Over the last, I guess, like 3 meetings, we've gone over all the details of this policy improvement through search algorithm, which uses this Dumble sampling based on this paper, which is a follow-up to the AlphaZero algorithm. But so far, we've looked at it in the MDP context, where we have like a set environment and we're trying to optimize performance in that environment, optimize, reward accumulation. And while you can use this algorithm for that, a large interest of this algorithm are self-play games or like two-player games where you can train an algorithm to play against itself and hopefully achieve stronger and stronger performance. And like some of the charts in this paper are showing examples of those sort of two-player zero-sum games. I'm sorry if I'm a little quiet. I'll try to be a little closer to the microphone. Like Go, this is an example of, well, like a two-player zero-sum game. There's also examples here of just MDP environments. Here, like these Atari games where you just have a player against the environment. And then there's more examples in the appendix here. But since we're sort of now connecting this back to multi-agent reinforcement learning, we're gonna re-examine the self-play scenario and how to apply it. It's actually, we had stopped looking at this textbook, but it's this section of the textbook where we really look at the search algorithm in the context of self-play. And really, we've already done most of the hard work of building this algorithm and explaining how it produces policy improvement. Really, there's just a couple of details we have to tweak for the self-play. And to look at it first, I'll just look at these notes I made. These are the notes I had from last time about the whole training pipeline in the MDP setting. So here, I've just added to them. So in red, like highlighted things that have to be modified for self-play. So initially, we have this idea that the search enhances the policy function. Now here I'm showing there's, from a given state, we have the policy function that's used to make action selection. Now here, the difference is that when we write this down, that there's a policy acting on the state, we're now considering games where these are turn-taking two-player games, where really on any given turn, like while in the game context, you can have simultaneous actions. So for the purpose of mapping this onto these turn-taking games, during any given turn or in any given state, one player is sort of active and they have an action selection to make. The other player also has to make an action selection to keep it consistent with simultaneous action selection, but they'll just select sort of a default action, which basically is a pass for them, And there are also games where a player may have a legitimate pass turn where they don't modify the state at all. And that would be the same in this case, where like if you're playing chess or Go, if it's not your turn, your action in that state has to be the sort of the no op action. So when we write this down in the self-play context, this is implying that we care about the policy function evaluated for the player who is active or whose turn it currently is. And then when we then, generate an episode, we also want to make sure that we have a way of keeping track of which turn it is in this episode, right? And this is now going to be a self-play episode where the policy function we're using is alternating, between making action selection for the player whose turn it is. Okay, any questions so far about this? So the next part of this, the main thing we have to worry about here now is we're still going to collect data. We're using the search as a way to collect data, fill up this replay buffer. Now, when we think about the training process, we need to make sure that the feature vector mapping we're using, where like we have like the states are the input value for the training process. And since we have two players, we want to make sure that we map the feature vector in a way that is specific to the player whose turn it is. That's going to be important. I'll explain in more detail later, but this is where these egocentric feature vector mappings come in, where because we want the same function to be able to produce values and action selection for both player one and player two. And for that to work, we need to present the feature vector to the function in a way where it's not going to have conflicting inputs. And then everything we discussed after that is the same. These details about the rate of generating data and what the composition of the buffer looks like. These are all things we discussed in the last meeting. You can go back to that. We're just looking at, we want to tune this generation versus training rate. We have some levers to pull, like the number of simulations that we allocate to the search, as well as the batch size we're using. And those are all things that we have to tweak in order to make sure that we have that we're not overtraining on a given amount of data. We don't want to overfit on a certain amount of data. We also don't want to waste data that we've generated. So there's some sort of reasonable range of values for this generation versus training rate. And then, okay. So this is all we discussed last time. Now, the goal of the training process is also different. So in the MDP setting and in just traditional reinforcement learning, we have a pretty clear-cut goal with a lot of nice theoretical guarantees, because we're just trying to optimize the performance in an environment that's the same as saying we want to maximize the reward we accumulate in a given episode. All of this whole MCTS pipeline does require that the environment we're in, whatever it is, if it's a game or not, that it is an episodic setting where there's going to be some endpoint to the process. And then this whole training pipeline we had in the MDP setting was consistent with that goal, where we're guaranteed to have this policy improvement. The improved policy, what makes it an improved policy is that it has a better average reward in the environment. So great. Everything is easy. We can track progress very easily, which we did. We can just look at the performance in the environment over time and use that to gauge, the training progress. Now, in the self-play setting, we have a very different goal, and most of the games we're looking at are two-player, usually zero-sum games. Now, if you have a fixed opponent, you can turn that into an MDP setting, and that's what we did in the previous meetings. And when you have a fixed opponent, you can always train something to optimize performance against that opponent. In fact, you can do that in a multi-agent setting as well by having just multiple fixed opponents and you keep trying to train against them. In the self-play setting, we're simultaneously training, both players in any given batch of data in any episode. So there's different ways we could say what the goal is. And these are all sort of equivalent statements with less degrees of precision to what they mean. But, intuitively, we want to optimize performance against any opponent that we might face. Now, this on its own doesn't really mean anything because, depending on the population of opponents, different things would be optimal. Another way of saying it is maybe we want to maximize the win rate against a worst case scenario opponent. So that means whatever we've trained, let's assume that someone else is capable of actually finding the most optimal opponent against us. And we want hopefully a policy that, does well or better than anything else that we can come up with, even against that worst case scenario opponent. This also is sort of the same as trying to find an unexploitable strategy. And that's really what the minimax solution is. All right, the minimax solution is a solution that doesn't have any weaknesses. It doesn't necessarily perform the best against every single opponent. if you have a given policy that is very weak, you could train a policy that would maximally exploit that weak opponent. However, that policy itself would have lots of other weaknesses. The minimax solution is one that doesn't have any weaknesses, meaning like there is no opponent that you can produce that will it is less exploitable against its worst case opponent than any other possible solution that you could come up with. And finding this solution is not necessarily straightforward. It won't necessarily work with this training method even that we've set up. It doesn't mean it won't work. It just means that there are algorithms we looked at in the past in previous chapters that were designed specifically like to find these equilibrium. I mean, the minimax solution is an equilibrium solution as well, because it's a solution in which neither player can change their policy and produce an improvement at all. So there are ways like you can get hints and check your training progress in a way to see like, are we in an equilibrium solution? Like if you have two policies and you try to improve one and you see that no matter what you do, neither policy can find an improvement, it's likely that you're in an equilibrium. However, the actual training process we're going to use for this, which is the same, this like, supervised learning on the search data, isn't necessarily going, guaranteed to find this equilibrium solution. I believe that's the end of that. Okay, are any questions about that? Now, in the textbook, there is this mention here. There's a nice illustration here in the book on what is meant by that like egocentric feature vector that I mentioned. So this is an example from chess where they define this transformation function. It takes a state and flips the perspective of the state for this player, right? So it means like if by default we have the state and we're assuming like this is like a state for the white player. If then it's a turn for the black player and we're in fact using the same policy function, then and value function, we want to then present the state to that function as if it's the same player, so that all its input output relationship is always consistent. It's always producing an output consistent with the current player input, as if like it's producing policies and values for, let's say, the white player. Then if it is the black player's turn, we want to flip the board or invert the board in such a way that there's an equivalent position for white, where white is in the same position in this state that the black that the black player was in. And then we can ask our function to produce an output from that, and it'll all be consistent. So that's one of the things we have to do. The other thing is that there are some of these update functions we had for the search where like this updates these action values, right? And ultimately we're going to use these action values. This is in like traditional MCTS. It's the same idea in the Gumbel version of it, where we're going to use these to judge which actions are good for the current player we're analyzing. So we really want these Q values to be from the perspective of the active player, right? So we're going to update this, and we have this signal, this U signal, which is the value we're going to use to update our Q values. So we also need to make sure that this value is from the perspective of the active player. So if it's like player 2, and we're getting rewards from the environment that are usually right in a zero-sum game from the perspective of player 1, we want to make sure we invert this value, take the negative of this value, so that we make sure the action values actually reflect the action values for the current active player in the game. Let's see, is there anything? Okay, so why don't we can look now at the code a little bit and how this works. So we're going to use the same environment that we've been using, this sort of extended tic-tac-toe example game. In case you missed previous meetings, yeah. It's just a game where we can arbitrarily decide the size of the board and what the win condition is. So for this initial test environment, this is a board where the win condition is 4 in a row, and the board is, is 10 by 10. And luckily, these games have been studied a lot in different sizes, so we actually know ahead of time some theoretical properties of how this game works. So now, in order to do this, the MCTS and the self-play setting, we do need a little bit of additional information than we have when we just do it in the MDP setting. So you'd see it's really, these are the 2 extra pieces of information that we need. And this is going to be passed into the Gumbel version of MCTS as well. So one of them is a function that tells us who is the active player in this state. Because then for the inactive player, instead of doing any kind of analysis with them, we're just going to have them use this pass move index. We're like, this is the move they have to make when they're not the active player. The reason why we have to add this is this normal game structure I've defined, this need to define who the active player is, like it already has a function that tells you what is a valid move for that game. And if you do any kind of training, it'll only select actions from the set of valid available moves. But in the case of doing, these searches, we actually need, like we want a more straightforward way of just identifying who is the current player. So these additional things, pieces of information will always be included when we have to do this kind of, this kind of self-play application of the search. Now, let's see. So this is an example of just building a strategy that uses this vanilla MCTS, right? Not the whole like thing enhanced with the policy function in this game, in the self-play setting. So now on every turn, alternating, now one of these searches is going to be performed, right, for each player according to, whichever one is active. Luckily, in this particular game, we can see what the game states look like. I changed this a little bit so that the active player is just stored in the game state. So, that way we don't have to do any kind of calculation to figure it out. This is probably a good policy in general because there are a lot of games where there is no way of identifying whose active turn it is just by looking at the state. Just be something that you're actually told explicitly. This game happens to be one where you can always tell whose turn it is because of how many pieces are on the board, right? But that's not a general rule. In a game like chess or something, that there's no way of knowing whose turn it is because you could wind up in a state like 2 equivalent states where it's one player's turn or the other. So if we look at, because this search is very simple, this self-play search, it should basically proceed where early on there's so many states here, this number of simulations isn't really enough to figure much out with it. So it should be like fairly random behavior. You could see that as soon as X starts getting moves that are close together, it's much easier for the search to identify without going too far into the tree that like, oh, this is much closer to a winning position, right, than if I move like over here somewhere. So I believe what's going to happen now is, like the X player just sort of got lucky and found this. But this at least verifies that our version of search is working, and at least when we get, close to a winning position, the search function should have no problem, figuring out those moves. Okay, so now if we go back to now the more elaborate version of MCTS, we're going to use where, we're also have this where is it? This function. So unlike the vanilla MCTS, right, this version of the search, this is like where we're enhancing a given policy function. this is this function that we're passing in all the time, which produces some a priori policy distribution for each state, as well as a value estimate. And unlike the other version of this in the MDP setting, right, we also have these two additional pieces of information. The thing that identifies the active player, as well as the pass, what is the pass move that we need the inactive player to use. And then the rest, so this notebook I made just parallels the one we had used in the previous meeting. I just went over building up all these functions we needed to do the search. And then I made this test. Yeah, so in order to use this, you do need one of these functions, this distribution function. Here I've just made one that basically provides no information. It's just random. And just to verify that it is in fact working at all. So at least, if this works, it doesn't crash at all. We can see that we get, a proper action selection out of using the policy function. Now here, in order to do this and actually, turn this into like a training, actually, did I think if we go back here, that there is one other thing. Yeah, so on top of those two pieces of information I mentioned, there is something else that distinguishes this from the other version. And that is that this function, when we construct it, it will account for these egocentric feature vectors. And this game state is very easy to construct a feature vector out of, right? All we really have to do, we can just have a numeric value for each square in the board. And we can have unoccupied squares have a value 0. And then the X pieces can have a value of 1. And the O pieces can have a value of -1. Now, since we want the feature vectors to be from the perspective of a given player, right, we actually want to use a different feature vector mapping for the O player. So now the O pieces will be mapped to 1 and the X pieces will be mapped to -1. And this is what allows us to use the same set of parameters, the same function to produce outputs for both players, right? Luckily, I intentionally chose a game environment where this inversion is very simple. In a game like chess, the inversion is a little more complicated with how you have to, rotate the board. And, here we don't have to worry about that. There's all this rotational symmetry. It doesn't really matter if we, Another option when you're, by the way, like using this to generate data and like filling up the replay buffer is if there are symmetry transformations in the game. Like in this game, it's symmetrical to a lot of different rotations, to mirror flips in a few directions. You can augment the training data as long as you have a way of changing the policy vector to match that symmetry transformation. You could potentially like 8x your data generation by just applying a symmetry transform to everything, right? Because it really shouldn't matter. All those rotations and flips shouldn't make a difference. So that is, I haven't implemented that yet, but it is an option to sort of enhance your, like, you effectively speed up your data generation rate by doing that, because you get all these transformations for free when you do those symmetry functions. So we had discussed actually previously these egocentric feature vectors in the context of training homogeneous agents, right? So these are agents where we again have the same parameters, the same function, select actions for both agents. And in order to do that, we need to change something so that the agent knows like it's supposed to be producing an action for player 2 instead of player 1. And the easiest way to do that is to do this sort of this alternative feature vector mapping, right? Where you say, we're going to present the function with the inverted features, and then we're going to train the function in such a way that when it sees the inverted features, it will produce, you know, the right policy for, for player two instead of player one. And that's exactly what we can do with like independent actor critic training. This was a training method we had before where we just basically do policy gradient and treat each agent as an independent learner in what is a non-stationary environment because the other player is also changing. This is an algorithm that we could use. It doesn't have very good guarantees of performance because both agents are learning simultaneously, and it's possible that you get cycling behavior. It really depends on the game environment how well the process converges. Um, but you can see here this flag I have when I call this um, this training function, where it's going to share the policy and the value parameters. Okay, this is only possible. Um, yeah, this is only possible in the context of having a separate feature vector mapping for the second player. I wrote this out a little. I already said this, but if you want to apply this to just more general games, like not just this tic-tac-toe game, but you have to think of the feature vector as answering the following question, which is that the information in the feature vector should be from the perspective of like its pieces versus the opponent's pieces. So for the X player, rather than thinking like, well, X maps to 1, O maps to -1, the way you would map the feature vector is you say the active, like the current player's pieces, or like the player that you're currently evaluating, their pieces map to 1 and their opponents map to -1. And that way, same with the positions, everything, whatever information is in the vector, it should be from the perspective of the player that you're going to ask the function to provide an output for. So then, actually, I have a copy of this because I think the training results were better here. So this does this independent actor critic training, and we can sort of track the performance over time. And this actually trained in such a way that player one has very dominant performance, right? So at the end of this training process where they're both learning simultaneously, um, player one is consistently beating player two. Now, we don't know ahead of time what the equilibrium condition for the game is, right? Like it could be a game where if both players play optimally, you end up with a draw. But that's not necessarily the case. So seeing that one player is dominating is not necessarily an indication that there's something wrong with the training process. That could just be actually what the environment is like. But we can get some sense of what's happening by then benchmarking the performance of this against some opponents after the training's done. So here, this is the performance of the self-play performance. So this means that player one is basically winning all the time. Now, we can also check each against a random opponent. So here we have the X player who is dominating, you know, its self-play opponent here against a random opponent, and it's also winning, very consistently. If we then look at the O player, this negative value means these performance values are all in terms of player one. So this means that even though the O player is being dominated, right, against in self-play, it actually has learned to consistently beat the random player. So there is some amount of learning that has occurred here, at least, some information, some indication that the training process has, learned something valuable from both players. And actually, we need the O player to have learned something because otherwise the X player can only get so strong, playing against a very weak opponent. So we can also visualize like an episode from this and see, what have they actually learned? What do the self-play games look like? And just show an example. So this game, apparently it lasted, 15 steps, and it ends with player one winning. Not two. I mean, almost all of these should end with player one winning. Um, Also, another important point, this was trained with a discount rate of 1, right? So a given player gets no advantage from winning faster. All that matters is that it ultimately wins. And that sometimes can produce some weird behavior, like if a player has sort of a guaranteed win, but they can, instead of winning, create a situation where they still have a guaranteed win. They may not actually just take the immediate win. So you can get weird situations like that. But, there are like good and bad reasons to train this in an undiscounted fashion. We could also use a discount rate very close to 1, which wouldn't change the results too much, but it would incentivize that, winning in a timely fashion. So we can see what this looks like. X seems to favor play in the center of the board, and the O player does its best to block around it, protect these double threats as they come up. So basically, like from this position, like the problem here is that, I mean, you might think like, oh, well, like why doesn't O play here? Because clearly X has this, potential double threat. And the problem is if O plays here, then X can play here. Basically, anytime a player gets 3 in a row that is unblocked on either side, then they win because there's no way to block both ends. So O can't really do anything about this. Here, like if O plays here, X can create this double threat here. And then, this is evidence now of the lack of discount rate because the O player, well, actually, no, it doesn't matter because wherever O plays in this case, they end up losing on the next turn. Now, this also highlights the how the discount rate, selection of 1 affects things. Because here, X has a guaranteed win, right? Playing either here or here. And we can see on its next move, it actually plays here, right? Which seems like a really bad move. But by playing here, it actually creates another double threat, which is blocked. And then by playing here, it creates another double threat. And then another double threat. And then it finally wins on this diagonal. So because of the way we've trained it, it could have taken the win on any one of those, but we can see just examples of it. It just keeps creating guaranteed win situations when it moves. Now, if you look, there actually is this type of game. There is this, in like research terminology, this is called an M by N by K game. So this is the size of the board, and then K is the win condition. So if we look at some specific results here, we can see that for the 4 in a row win condition, M by N by 4 is a win for a large enough board. Although there are some weird cases here, like if okay, I'm not actually sure. Oh, sorry. So this is if the board is small in one of the directions. But if the board is large enough, and 10 happens to be large enough, then this is a guaranteed win for the X player under perfect play because it's just too easy for them to create threats. So, we didn't know that ahead of time necessarily. But it does mean that if we're tracking the performance of this training process, if these actually find the minimax solution, which is possible, then we would expect player 1 to dominate the performance, right? Because the actual minimax solution of this is that player 1 wins, can guarantee a win every time, right? We would hopefully also expect the player 2 to have a good strategy where if X makes 1 mistake, maybe player 2 can capitalize on it and win. But especially if we've trained this without discounting, the O player might get into a situation where if it knows X is in a position where it can guarantee a win, which in this case is actually for move 1, it may end up playing, random moves until it learns otherwise that X indicates that maybe it's not, a perfect opponent. Because, again, like in the equilibrium state, this is going to be a situation where O simply, player 2 can't do anything against X. Like whatever changes it makes to its policy, if X is in that perfect policy, it will lose every time, right? So if O was actually training against the optimal opponent, that Minimax player, it wouldn't be able to learn anything because, right, it can never produce a situation in the training data where it has a win. So yeah, the training process we're going to use the search is not the same as this independent actor critic thing, although it is sort of similar. It's not quite the same as independent learning, but it does share the same properties of having the homogeneous agents and the feature vector inversion. But even just using this method, going back and forth, they do seem to arrive at this equilibrium where this is probably still a strong policy because X seems to have learned here how to play enough pieces in the right configuration in the center of the board where it can always create a double threat at some point, right? This seems to be a configuration where it can always make a double threat that O can't block. Okay. So any questions about that? So once we've trained, right, with this method, we have now a policy and value function for with that share the same parameters. Now, before we try to do the full training pipeline, we can actually just try to take that. So here I've made this like test this from the actor critic method and say, okay, take the actor critic function, and for the purpose of doing the search, enhancement, let's use this function, its value and policy distribution, and see if we can enhance it with search. So here, this is going to make a search enhance policy version based on the actor critic solution that we already had. Now, what's interesting about this is like we know, right? We know that player one wins in self-play. And the idea is that if we allocate search iterations to it, search simulations, we can then strengthen the policy. So what this does is it says, okay, let's take the search enhanced policy. And what if we allocate, fewer simulations to player one than player two? Right here, so I've actually increased the number of simulations. So I'm basically strengthening player two more than I'm strengthening player one. And as a nice way to verify that this search enhancement is working properly is that we should be able to actually equalize the performance between the two policies by doing this. So here, by sort of over allocating simulations to player two, this is now the performance, or like, a performance value of 0 means that on average, they're either reaching draws or the wins and losses are equal to each other. So this is a nice indicator that at least like the performance is scaling up with the number of simulations. Again, now, interestingly, if we now run this where we have an equal number of simulations, we don't get the same performance that we did before. We actually get much closer to even performance, right? Player one is now not dominating as much, which may mean that, I don't know, like the search just exposes more. It equalizes the performance a bit because it does a better job of enhancing the weaker policy. But then we can also compare, again, another verification to make sure that the search is working. What this is showing is, what if we play the search enhanced policy against the original policy, player two original policy, which we already knew dominated. We can see here a nice verification. Okay, this means that it wins every time. We can also flip it and say, let's take the actor critic player 1, which we knew was strong, was dominating player 2, and play it against the search enhanced version player 2. And we can see now this value of -1 means it's now losing every game, right? So that means that with enough enhancement of the original policy, we can actually tip the scales, kind of like we did here, to equalize it. We can also tip it so much that we make, the other player arbitrarily strong, right? So this like reverses the result we had from before. Now we can see now what it looks like when they play each other. So this is showing when we give each an equal number of simulations, quite a lot of them here. I'm using 800. And we can see what this game looks like. What I'm showing this, the heat map overlay again is the original policy function. Yeah, the original actor critic policy function. So sometimes if the moves deviate from that, it's because the search policy is causing the deviation from that. So here's an example where like normally the policy function would play here, right? But the search function is actually playing here instead. And same with X, right? X would normally play here. The search function is playing this move instead. And we can see exactly what's going to happen here. Okay, so now, I mean, again, unfortunately, this still is a situation where on the next move, X could create a double threat again, like whether O played here or here. Like basically, wherever O plays from this point, on X's next move, it can create one of these, 3 in a row threats that is unblocked. Like it could have also played here, and that would have been a diagonal 3 in a row threat. But then X again goes and does a little bit of trolling where it just keeps creating more double threats, even though it could win. So here it could have also won by playing here or here. So yeah. Anyway, this X, player 1 still wins this with the search enhanced policy, and they both appear to be playing, reasonable policies with the search. Okay. Now, in terms of now transforming this into a training pipeline, we have like the same stuff we looked at before where we have the data collection. We build batches of data. We do supervised learning. The one little difference we have to look at here is when we generate the training data, we have to make sure, since we've inverted the feature vector, right, and we're using, the same parameters for both sides, we do want the value target to make sense. So if that point in the data set corresponds to player 2, we want to actually invert the value target, which by default, the values that's being collected is the value from the perspective of player 1. So that's one difference. And then we also have to make sure that the feature vectors that are being stored in the buffer are alternating, where we're getting the inverted features where they're relevant when we have to make a selection for player 2. Yeah, this first part is showing the supervised learning part of it, where we take we fill the replay buffer with data from the actor critic policy, but we can skip past that and go to the actual training loop here. Here again, when I define this, normally I have to add this extra information where this is the function that tells it what the current active player is. And then this is the pass move. It's indexed 101 because the board is 10 by 10. So basically, any action index from 1 to 100 is a move on the board, and then 101 is just the pass move. Now, okay, so this is showing training. Yeah, yeah, interesting. Okay, so now when this training process is going on, there are a few different things being evaluated here that are also different because now we can just train for multiple generations and we have to decide, when to stop. What is a good criteria to verify that we're still improving? And there's a lot of different things you could do, and the situation can get very complicated. And what's being reported in here is a combination of information that I decided on, and it is partly based on what actually comes next in the book, which is this section on population-based training. And the reason why I looked at this is because when we look at this training procedure, and you look back at my notes where we have the replay buffer, right? We have different generations of policies, and they're hopefully getting better in some sense. And in the case of the MDP training, their performance should be improving over time. In the case of self-play, right, we could have intransitive properties where like generation 4, player 1 of generation 4 beats player 2 of generation 3. But then, player 1 of generation 3 is somehow stronger than player 2 of generation 4, stuff like that. So we have these like incompatible things that don't allow us to just say one policy is strictly better than another. However, we can think of it as all these generations form a population of different policies that we've trained. And the question is, what do we do with these populations? So this thing, in our case, our method of having populations is from the replay buffer and the search enhanced data and training generations of policies that way. This section of the book looks at there's different algorithms where you can train policies. This is not using MCTS at all to do that, but there's an important concept in this section related to population training, and that is this metagame concept. So the idea behind the metagame is that you think of all the generations and you form a new game, a metagame, from their performance when you match them up against each other, right? So what this matrix is showing is like, what is the return, or like what is the episode outcome for player 1 and player 2 when this matchup occurs, right? So we have this matrix of generations. And this looks a lot like what we had, in game theory. We can create a game with this payoff matrix. Now, the idea behind the metagame is to say, okay, we have this information about how all the different policies match up against each other. And the question is, how do we want to use this information? Well, or how do we want to, evaluate what, which policy to use? Like, how do we say which is better? And one way of doing that is say, well, let's say that we could actually sample from the generations. Like if we're this player, if we're player 1, rather than selecting one policy, we can say, what if we have the freedom to choose different policies according to some distribution, right? So like maybe half the time we select this policy and then 10% of the time we make this one. And then can we actually get a better outcome? Like we can actually calculate for a given distribution across these policy generations, how does that perform against a similar distribution against this set of policy generations? And in the case of a 2-player game that's a zero-sum game, when we have a matrix like this, a payoff matrix, where then these values are going to represent the payoff for player 1, right? Player 2 is always -1 times that. Then there actually is a unique solution to this metagame matrix, which is itself a minimax solution, which is an equilibrium solution, meaning that if I select policy generations according to this distribution, then and my opponent does the same, so we're both following the minimax solution, then we're in an equilibrium where neither one of us could change which generation we're using and produce an improvement. Now, if the metagame is really straightforward, like let's say each one of these shells, right? Like as we add a new generation here, this is showing like we now have to calculate. We have a new policy generation, all of these matchups, right? We have to add all the paired results from pitting this generation against all of these. And then we get a new set. Well, we expand this matrix, this metagame matrix. If you saw that the metagame solution said, well, after this much training, the minimax solution is to pick this generation and this generation, 100%. And let's say that kept going throughout the training process. That would mean that you can definitively say at every new generation, this is a better generation. Because like this is the only one we need to do, to have the most unexploitable strategy that we could have. But you could also get situations where you're still including maybe this generation still has some value, right? Now, in addition to this, to solving this, right, we get this solution where this is showing like the distribution across generations. We also get a value, and we can see how that value changes over time. Now, if we train for a while and we see that the metagame solution isn't changing, right? So that like the same generations are being picked, we're on generation 100 of training. And the metagame solution says, well, you should use, generation 5, 10, 20. And for the other player, it's some other set of generations, but they're far from 100. And then the metagame value isn't changing. That means that all the new generations you're adding, they're not being used. Like they have no purpose in the metagame, right? Like in other words, you would never select them playing the metagame, where the metagame is like, I'm going to send you out into the world. You have to pick one of these policies to use to get your best outcome. And if you're training and you're not using any of the later generations, it means, your training is no longer producing useful improvements. So what's being shown here as these generations are being trained is it's showing the metagame minimax value, right? Which is when both players select the best generations they could, what is the ultimate outcome? Now, we already saw for this type of game, right, this 4 in a row win conditioning game, this actually, with perfect play, player 1 should win. So we kind of expect the metagame value to approach 1, because that means we are getting close. But if you didn't know that ahead of time, you have no way of really knowing what this value should be. Now, this is showing the equilibrium policy. So this is like part of the minimax solution, is which generations are being selected in the metagame. And here it's a sparse vector. I'm writing it because we only care about which generations are active. This just means that it's picking 21 and 21 with 100% probability, which is kind of good for the training process, because ideally we don't want to see a big spread across generations, because that means that we're not really getting definitively stronger generations. But it is an indication there might be something wrong with the training process. We can see as this goes, you can see this is like 21. On this step, it's 22. So this means that this training is producing stronger generations. We can see periods where it's mixing up a few of them, although the metagame value still is not changing. And as we go down here, we really run into a problem, or like a failure case. Like if we didn't see in which generations are being used, like here it's, 60 is the one that was just trained, right? And we can see 60 is in the solution. So that means that the new generation is valuable. So this, I cut off training after an arbitrary number of steps here, but you could also let this keep going until you fail to have an improvement produced from the generations. So let me see. I have another example here of this training process. The same idea here, right? This report of generations. So at the end of this, this is now like the payoff matrix for this particular round of training. We can see here each one of these is the result of like the average performance we expect when these matchups occur. So when we start out, this is generation 1 playing against itself, and its value is close to 0, which means, with random play, we would expect, that the average outcome is close to 0. And this value 0.98 means in the latest generation we trained, that player 1 was dominating. Again, that's consistent with what we know is the minimax solution. We could sort of see a heat map of what this looks like over time. This is later generations in the upper right corner here in this heat map. So what this means is that if we go down this edge, right, this means we're using the latest generation of player 2, right, the most recent one, and we're looking at how it matches up against all the previous generations of player 1. And if we get to the bottom here, where this flips and becomes close to -1, this means that this far into the training, even though player 2 is really struggling against later generations of player 1, we have some indication that it has learned something, it's somewhat strong, because it is dominating still the early generations of training, right? So like we should see this happen. Now player 1, if we go back, it's dominating all the way through. If we go back, it has 100% win rate against the early versions of player 2. So this is just an example of a smaller version of this. These are just the first few generations of the payoff matrix. Now we can also see the policy itself over time. Let's go back. This is what I was showing is this is going to show not just which generations are being used in the solution, but also what the actual like distribution looks like. And we can see in the early part of training here, what this means is that we're on generation 5, and the metagame is saying, okay, well, the best thing you can do is use generation 5 for both policies, right? So very straightforward. We have an indication we're progressing in the training. If we go forward a bit, also to 15, same thing. So in all the early generations, we have this very straightforward improvement in performance. Now we'll have periods here like where player 2 didn't improve, right? Like whatever player 2 learned on this generation, it was you're better off using the previous version, even against the new policy. Right? Because this is looking at the current full metagame, accounting for all of the available generations. So if you see this happen, right, this where 1 is on 18, 1's on 17, it means that you just had a generation of training where the function did learn something useful for the first player, but maybe it was a step back for the second player. It doesn't mean that the generation was a failure. It just means that like we can see on the next generation, player 2 then caught up, and they actually both, player 2 caught up where they're both using the current generation. And if we keep going with this over time, we now see less straightforward situations where we get other policy generations mixed in. And, if there's just 1 in the vector, the probability is going to be 1. And as we keep going, like, you can always track this and see, okay, now there's like a mixture of generations. There's like this one back here. But also when you're done with the training, you can use this information and say, okay, I shouldn't actually just deploy the current generation of player 2. I should actually maybe, selectively, like, sometimes use this one or you use a combination of them. This metagame really says when you go to play an opponent, select this policy ahead of time, right? And the idea is that both people have the freedom to select, you may be playing against generation 25 or 35. And in order to deal with that as player 1, you have to then select with this probability from these generations. Another idea is you could even within a game switch which policy you're using, although that is not the purpose of this, because it's possible that one strategy is incompatible with another. So like this strategy, this policy would get into game states where then if you try to make an action selection based on this one, it isn't prepared for that. It could be they're all robust enough they could handle switching policies. But this whole display here is an example of how this metagame concept, like this matrix, is exactly analogous to what is shown here in the book. Although there's single values here, right? Because this is a zero-sum metagame, and this is a general sum metagame where you have two different values. Now, for the general sum game, you want to find a Nash equilibrium, which can be very difficult. There might not be any, and also non-unique. The nice thing about the zero-sum metagame is that we can really efficiently compute a solution. Here you can see it's been done for hundreds of generations, and it's a unique solution. So it makes it a great way of tracking progress. And so at the end of this training process, we have other data that we can look at. So this is now plotting the metagame value over time. So we can see this is trending towards a situation where player one is dominating. We can also see the progress of each player, which means for that new generation, if we compare that new generation to the previous generations, does it perform better than the previous best possible outcome from its minimax solution? So if this is a high value here for player two, it means that the most recently trained generation of player two was able to then exploit the previous generation, was able to find a weakness. And this is another indication if the training process is working. And it's information you can extract from the performance matrix. Or like we have layers of this matrix. So it's sort of like looking at not, like we have the full new solution when this is all filled in. We can also say, okay, now that we've trained this new generation, what if we pit it against what was the best solution that its opponent could have done, but only using the previous generation? And we can then see how much of an improvement was there over the previous metagame value. So that's another way to track progress. This is sort of looking at those layers of the performance matrix. It's looking for player one and two over generations, where now this is for player one, its performance. So this means like this is looking at the first few generations, and it's saying now against generation 5, it's only doing this. But if these lines are basically stacking on top of each other, going up in this direction, it means that every time we train a new generation, its performance is improving against all of the previous generations relative to the last time, right? So this means like if we're playing generation 4, well, the new one we trained is better against generation 4 than generation 4 did. And then similarly, this is for player 2, where these values should be getting more and more negative over time if the training process is straightforward, because this is indicating that player 2 is then improving against the previous generation. But these are all complicated heuristics, like looking at these lines. What's happening here in the training loop is that it's looking at a few different criteria to decide if a generation is like a failed generation, meaning like it didn't produce any useful information. And that is that a combination of multiple things, which is that the minimax policy didn't change at all. So there was no change in which generations are being selected here. And that there was no improvement according to this criteria, where like if we look at the new generation and see, did it learn anything exploitable about the previous minimax solution, that also comes up with nothing. So if all three of those things happen, right, if the minimax solution doesn't change and the new generation isn't able to exploit anything about the previous ones, then that's like a failure. This would be equivalent in the MDP training setting if the performance didn't improve, right? Because for MDP training, we're just trying to get better and better performance. it's much easier to deal with. So if the performance doesn't improve, that's like a failed run, and then we can keep going. And if we accumulate enough failures, maybe, the training process is finished. In this case, we have this much more complicated criteria that depends on this, metagame matrix, where we're looking at this interaction between all the generations. So, any questions about this criteria and what the metagame means? It is also possible to take this matrix, um, shown here, and use the information in this matrix to sort of calculate a rating for each generation. Right? This would be equivalent to, like in chess, like an ELO rating. There's a way to iterate through all these matchups. Like we've already collected the matchup data, so there's a way to iterate through this matchup data and calculate. That there's an iterative process that computes an equilibrium value that equates to a rating for each player. We could see it's not perfect because if you have in like non-transitive relationships, the ELO rating doesn't necessarily work properly. But this is showing an example of, on top of those other criteria we can look at for training, this is like looking at each player's ELO over generations. We could see, it's improving. So this is another indication that the training is working. And we can also see how valuable the ELO rating is, because we can use the metagame matrix to then compute the ELO that is most consistent with it. That ELO then also predicts the performance matrix. So we can see how close is the predicted matrix to the actual one. And this R squared value is one measure of how close. Like if it's 1, then it's a perfect prediction. So this is an indication of how relevant the rating is. If it's like the closer this is to 1, the more these ratings reflect the true strength of each generation, the more it's relevant in evaluating whether the training process is working successfully. Yeah, because like really what the ELO does is it gives you a way of predicting the win rate if two players play each other, right? So there's a way to equate, all of the simultaneous win rates to the rating. The reason why there's two values here is because actually when you have games where there's a difference between the two players, like this is one where clearly the O player is different, has different expected results from the X player. I think it's more useful to have a separate rating for each perspective in the game. Like in chess, this isn't usually done. Usually white and black, like you share one ELO rating for playing with both white and black, but really black plays differently than white. So to get better information from everything, it's probably better to rate each side like separately, because you may get situations where one person is actually comparatively better playing from one position than another. So that'll allow you to see that. Now, I think the other thing, once we have this solution, oh yeah, so this is an example of actually seeing what at least this training solution did in terms of what the episode looks like. This is an episode where X1, I haven't looked at this yet to see what the actual policy looks like. Yeah, so now this policy function is then what's been trained from the MCTS. Again, it looks pretty different from what we got in the actor critic method, where we had a much stronger probability concentration in certain moves. This, we see the probabilities being distributed among more moves. Yeah, and we could see a lot less effort to reduce moves close to each other early on. Of course, this training process also hasn't converged yet. So it's possible that this episode just looks, yeah, I mean, clearly this hasn't converged, because if it did, O would have made an attempt to block this. It's also possible they're just playing kind of over our heads, where because the metagame is so dominant for X that O already knows from this position. But actually, no, I mean, this is clearly not converged properly, right? Because O should have already won from this position and get 4 in a row. So this just has to train longer. All these episodes we run, we should see that because we know the metagame value, they should all end in X winning just because that's like the dominant, um, like that's the outcome of the self play. So yeah. So going, beyond this, there's other we can look at other variants of the game. Like there's if we look at this, there are other versions of this game where if there's 5 in a row win condition, it's more like a draw win scenario. And that is something where we could see a very different metagame situation, right? Because we would have a much more even performance across the diagonal here. So that's something else. And then also what I did so far is sort of an initial look into this metagame training and population training. The idea is, again, the same as just tracking these generations. But we already actually covered the aspect of this chapter where we solve the metagame for the generation we happen to be at. So probably next time we'll look be more at refining this or like seeing what the training looks like to convergence and also in different variations of the game. And then starting to look more at this section of chapter 9 where we do more with the metagame training. And this is like the last part of chapter 9. But yeah, this sort of population training, it also, we can see there's a reference here to this other DeepMind project, Alpha Star, that involved populations of agents, not necessarily with the tree search like I've done here, but it is another example of a, sort of not exactly self-play, but play between generations, right? Here, all these, we're also evaluating not just like the self-play is occurring within each generation of training, but this matrix is showing, this full population, matchup that we have. We can see what the population looks like over time. So any other questions about this or about what we're going to get to next time?
I did not have any question regarding the metagame with the population, with the metagame about model type, well, model generations.
Mm-hmm. Okay, great. So yeah, next time we'll sort of finish this up and maybe be able to finish chapter 9 as well. And then after that, there's a few case studies and things, but we can also discuss, or I can make a post in the meetup too about other, things people might prefer to move on to. But yeah, if you have any suggestion about what to do, what to cover, or a particular case study you'd like to see tackled with any of these techniques, you can, write a message there in Discord or, yeah, or, as a comment on the video recording as well. So yeah, thanks for coming everyone. And yeah, hopefully see you next time.